We do have our homework due tonight, and I will just remind you, our first quiz will be on Friday. So the quiz always covers the same material that was on the homework, and the quiz questions are always specific to the big list. So this time we will do questions, the first 3 questions on the big list. The first one is just basic integrals and derivatives. The second one is the U substitution, and the third one is area between curves. So you should expect 1 question about each of those 3 things. And hopefully you'll get the full credit and you won't have to do it again in the future. Any questions about the quiz? Like, I intend to do the quiz just, we'll do the quiz for like 15 minutes or however long it takes at the beginning, and then we'll just go on with class immediately after that. Yeah.
So there's no volume, right?
There's no volumes, yeah. That will be on, like if you didn't see it on the homework, then it's not gonna be on the quiz. So that stuff is gonna be on next week's assignment. Yeah.
Will you like give us the graphs for like the equations to find area?
Yeah, mostly yes. So I would expect you to be able to draw a straight line or like a very simple parabola, you know, like x squared plus 1 or something like that. But the ones, especially the parabolas in terms of y, I wouldn't expect you to draw those. I would either, you know, not give you one of those or draw the picture for you. All right. All right, great. I am going to have you hand in the quizzes with Gradescope, so be ready to do that. Hopefully hopefully the like Wi-Fi or something will work out okay. All right, great. Let's continue then. So last time we did the volume with the washers thing. Today I want to do the other volume topic, which you will see on the list. This is called volumes. It's very similar. Volumes with cylindrical shells. All right. This is another way to find the volume of a revolved solid, and it's basically just another method to solve the same problem. So, typical problem about finding the volume. You could do it using the washers, or you could also do it using the shells. And for various problems, sometimes one or the other of the methods is easier. For our purposes, I think it's interesting to talk about just because the cylindrical shells, the idea behind it, the setup of it is quite a bit stranger in my opinion, but it's a nice example of how you can use the integral in somewhat weird ways. So anyway, here's the idea. I'm gonna, just as an example to talk about. Let's talk about the parabola. But I want this, you know, this part, and then revolve that around the x-axis, the y-axis, I mean. All right, so spin this around. What you get is sort of like, from the outside, it would look like a cylinder, but it has this parabola sort of like drilled into the middle of it. All right. If you were looking at it from the top, it would look like a cylinder, but then the inside of it is like some sort of a basin in there, right? Does that make any kind of sense, that picture? I don't know. Yes?
Is it touching the x-axis?
Yeah, this parabola, so technically it is touching right there, so the bottom of this thing, if you made this in real life, it might have like a little leaky point at the bottom. All right. Anyway, I want to find a volume like this. Now, you could do this using the washers. And the way you would do it would be do your slices this way, and you would get washers with an inner and an outer, and you would do your variable with a dy in that case, because you're slicing this way. You could do that, and that would work. You'd have to change the function. Instead of y equals x squared, you would write it as x equals square root of y, and do the washers thing. Or instead, you could do it with cylindrical shells. So the shells strategy. You are also going to, of course, sort of slice up this three-dimensional figure into shapes, but it would not be possible to make these slices like with a knife. So the slices that I'm going to make are not actually sort of straight line slices. We slice, maybe you shouldn't even use the word slice. A slice, does a slice have to be straight? I don't know. We are going to carve if you will, this thing into cylindrical shells. They would be shapes like, if I took, so I will draw for you one of these shapes. You sort of make like a rectangle like that, as if you were doing an area under the curve, but then that thing gets revolved around the x-axis. So the individual shape, one little slice of this thing, looks like that. It is a cylindrical shell. It looks like a cylinder, but sort of empty on the inside and has a little bit of thickness. So the shapes that we're slicing into look like this. All right, it's like a tube, right? Those are the shapes. We slice this thing into shapes like this. So there's one sort of, and these shapes, they kind of grow from the inside out, right? So there's one very little one in the middle, and then we gradually increase the radius until we get all the way out to the outside. All right? This is the cylindrical shells strategy. It's weird because that thing is curvy by itself. It's not like a flat thing. But when you're using the integral to do little bitty bits, those bitty bits can be really whatever shape you want. You could invent your own strategy for carving something up into a bunch of little bits. In this strategy, the little bits are cylindrical shells. Very strange, but it's going to work out fine. So we are eventually going to turn this into an integral. We need to figure out what is the volume of each one of these weird shapes here. So let's talk about that. Each such shape, so if I were to, let me just draw another one of these like that, right? Sorry, it should have like a uniform thickness, all right? We should try to think from the original picture, where do the various dimensions of this thing come from? I would say the important dimensions are the radius, right? Now, technically it has an inner and an outer radius, but actually I'm not going to think in terms of the inner and the outer radius for reasons which you'll see in a moment. It also has a height, right? And it also has a thickness, the thickness of the shell. Now, from our original picture, you can see the thickness of the shell comes from the thickness of this little rectangle, which, as usual, I'm going to call delta x. So there's the thickness of the shell here, which is delta x. And that's why, actually, I'm not going to talk about the inner versus the outer radius, because, of course, when we make an integral into this, we're going to basically make the delta x become 0, in which case there would no longer be a distinction from the inner and the outer radius. There's really just the radius of this thing and the delta x and the height. Where do these various things come from in the original picture? Can anybody say, where does the h come from in the original picture? Yeah? Yeah, in this example, it's x squared. Generally speaking, this h refers to the height of the function. So this is just going to be f of x, whatever that is. If I was doing this particular example, it would be x squared. All right, the delta x, I'm not going to try to plug anything in for that. That's delta x, which in the integral will become dx. What about r? Where does r come from? This is a little weird, but r just represents like how far across that is, right? And that's just x. So r in this case, I didn't really leave enough space in here. R is just x, all right? As the x goes across the picture, whatever the value of x is, that's what the r is, all right? And now, what is the volume of this kind of cylindrical shell? So each shell volume, this is another weird shape that you could sort of look this up. What is the volume of one of these shells? It is, I'll just tell you, it's the, you think of this as if you had this thing in real life, you could like cut it down here and then flatten it out, and it would be a rectangle basically, all right, with some thickness. And so that rectangle, if you think about, so its height is h, and its width, once you roll it out, is the same as the circumference of this circle. So the volume, each shell volume is basically the height times the circumference times delta x, that's the thickness. the height times the circumference, that would give you the area of this rectangle if you rolled it out. And then you gotta, if you want the volume, you gotta multiply times the thickness. And what is h? H is f of x. What is the circumference? Well, the radius is x, the circumference is 2 pi r. So the circumference is 2 pi times x. So this is f of x. This is 2 pi x. And, well, the other delta x is just what it is, all right? This is delta x. So the whole thing, the volume of each shell, I'm going to always write it this way. 2 pi x f of x, delta x. All right? This is a somewhat weird-looking formula, which I would suggest you don't try to think through all these details. Just remember this is what it is. And so the volume of revolution formula is integral from a to b. And usually I'm going to, just like with the other one, I'm going to factor the 2 pi out of the integral because it's just a constant. And then inside is x f of x dx. This is the cylindrical shells formula. As far as formulas goes, like I said, any problem like this you could do either with the washers or with the shells. Why might you want to do the shells? Well, this is, in a lot of examples, easier to handle because the washers involves a square, which sometimes messes up your function. But this involves multiplying times x. Now, sometimes that messes up your function, but sometimes this is easier. So it's just a matter of, in each situation, deciding which one is better. All right, this is the volume for the formula for the volume of revolution using cylindrical shells. Now, one little technicality to say about the A and the B. So the A and the B, you will notice, when I do this, each shell actually occupies sort of both sides in terms of, you know, the right-hand side and the left-hand side. Like each shell actually includes both of those. So when you do your integration boundaries, you start from the middle and go out to one side. This is because each shell on the right side is like already including the value on the left side. So the integration boundaries should not be all the way from the left all the way to the right. Then you'll get sort of 2 times the correct answer if you do it that way. Instead, you want the middle out to the outside. So I will say where this is a little something. This is different from the A and the B when you're doing the washers. Don't work this way. So I will say x equal A is sort of the, maybe I'll say innermost beginning of the shape. The innermost edge of the shape. My example doesn't really have an innermost edge. It has a middle. The innermost, I'm going to say edge instead of beginning, sorry, to erase. And x equal b is the outer edge, right? With the washers, I would say this more like the left edge and the right. This is the left end point and the right end point. This is more like the end point on the inside and the end point on the outside, right? This is slightly different. Not such a big deal though. Okay. So can we just try this example that I've been talking about here? This is a fairly simple one. I'll draw the picture again. It's like that. This is x squared. All right. Don't be fooled by the -1 and the 1 that I drew there. Actually, the integration in this one goes from 0 to 1. The middle or the innermost inside all the way to the outside. So I'm going to go 2 pi, of course, 0 to 1. Inside there, x. That's just x. And then f of x is x squared. All right? Your friends at dinner might say, why you got to put the x in there? You say, I don't know. That's just the formula. If they really want to talk to you about it, you say all of this stuff, right? But it's not worth remembering all of this stuff. The formula for the volume includes the x in it, all right? And now we do the integral. We should just, actually multiply them first. But this is going to be a simple integral to do. X cubed dx. So it's 2 pi, 1/4, x to the 4. I plug in the 1. I think I'm just going to get pi over 2, right? 2 pi times 1/4 times 1, which if you want to simplify is pi over 2. I'll write that out. 2 pi times a 4th times 1. poverty. All right. Any thoughts about that one? This is a little weird, although, I mean, once you know how to set it up, it's not any more difficult. All right. We're going to do some variations, of course, but let me just do 2 more examples, and then I got one for you to try, and then we'll talk about some slightly fancier ones. Any questions so far? All right. Let's try. Okay, how about this? This is a triangle. And I want to rotate that triangle around the y-axis and get another one of these kind of Christmas tree stand things. My toothbrush stand looks like that. I got a nice electric toothbrush for Christmas. This is amazing. My wife got it for me for Christmas. Today, it ran out of batteries for the first time. I was pretty impressed with that. But I had to like brush it like a fool because it was dead and I was in the middle of brushing my teeth. Yeah. Still worked though, I think. Okay, find the volume of this thing. All right, again, you could do this using the washer method, or you could do it using the shell method. We're talking about the shells today, so let's do it using the shells. So it's going to be my formula, as always, 2 pi integral a to b x f of x dx. We should talk about the a and the b and also the f of x. The x is just x. You don't have to do anything with that. Let's talk about the a and the b. Anybody want to tell me what should I use for the a and the b? These are, yeah?
1 and 2.
1 and 2, yeah, the innermost edge and the outermost edge. Don't even think about this stuff over here because the shell sort of built into it is already doing both sides at once. So the a and the b in this case are 1 and 2, all right? What about f of x? Here you got to sort of figure something out. But, yeah? 2 minus x. Yeah, how did you get that? Mm-hmm.
And you just extended the y-intercept.
Yeah, great. This line is what you need to be concerning yourself with for the f of x. You have to find the equation of that line, which, you know, there are several ways you can find the equation of the line. What she said sounds like a good idea to me. If you just imagine that it extends all the way up here, I think it's pretty clear that that line has y-intercept of 2, and its slope is -1. So with the mx plus b business, it must be minus x plus 2. I think that's what she said. Or she said 2 minus x, same thing. Yeah, great. Okay, let's just plug them in, work it out. So this is 2 pi integral 1 to 2 x, and then f of x is, all right, like she said, 2 minus x, like that, right? And we got to do this integral. You should distribute the x first because you can't just take the integral exactly like written there. Distribute the x. So it's going to be 2x minus x squared, right? And now we can do the integral here. 2x becomes x squared minus 1/3 x cubed, plugging in 2 and 1. So that is whatever that is. 2 squared minus 1/3 2 cubed minus 2 pi 1 squared minus 1/3 times 1 cubed. There you go. Right, on our quiz I will expect you to leave your answers looking like this. This problem isn't going to be on the quiz, but if you're ever concerned on the quiz, can I leave it like this? You can ask me. And I'll say, yeah, probably. All right. That's the shells method. Let's just do one more. How about let's just, this one actually the integral is a little hard to do, but let's at least set it up. I would like the first lump of y equals sine of x and rotate this area around the y-axis. Like that. All right? Can anyone describe what this shape looks like? Yeah?
Start
I don't think it's not like this only round, because I'm rotating around this line. It's there's the other, the other half of it is over here, right? I did this in once. Somebody said, "Is that like the butt?" No, something is very wrong with you if it's not. Anyone have another idea? Yeah?
Like a bundt cake?
Yeah, it's like a bundt cake, like a coffee cake kind of shape, right? I don't know how to draw that any better. It's, sort of this kind of a thing. Nothing I draw will look good, but it's like one of those round cakes with the cavity in the center, right? Yeah. Yeah. All right, let's find the volume of that. Can we do it? Set it up at least. You'll see why I'm saying set it up. Actually, this one, the integral ends up looking weird in a way that is not convenient to actually calculate the integral. But let's try it. So we go 2 pi integral a to b x f of x dx. This is like a bund. All right. What do you think? Can somebody say what do we use for the a and the b? Actually, we should, first of all, it's going to be important. Where is that point? Any trigonometry masters out there? Yeah?
Pi.
That would be pi, yeah, if you know what the graph of sine of x looks like, which I hope you do. This is x equal pi, also known as 180, but I'm not into degrees. All right? Okay, great. And so what are the a and the b going to be? 0 and pi. Yeah, you want to go from the middle, or from the innermost edge, which in this case is just the middle, out to pi. So I'm going to use 0 and pi for the a and the b. And then x. And then f of x is just my function there, sine of x. All right? It is now set up. Actually, this integral is not easy to do. This requires a trick called integration by parts, which we're going to do eventually in this class, but we haven't done it yet. So I'm just going to leave it at that. I will just say this is now a tricky integral to do. So let's not bother. Actually, this is an example of one that you can't really do with the washers, at least not in any very convenient way. You would have to do some really weird tricks to do with the washers, because if you, the natural way to get washers would be by slicing this way, but you will notice that there's no nice inner and outer. Like the inner radius is determined by this function, but the outer radius is also determined by the same function again, which is going to mess up your washers formula. So this one actually, you can't really do with the washers unless you play some serious tricks. And so the shells is your only way to go. All right, I got one for you all to try. Yeah, sure. How about the shells? Find the volume. This is going to be that's a part of a circle, like a 1/4 of a circle, right? This is a quarter circle. That is 1 and 2. And then I want this to be revolved around the y-axis. So this vaguely looks like another kind of bundt cake sort of thing, although with a flat edge on the outside. All right. This one you'll have to work a little bit. To figure out the function there, but maybe I'll let you think about that. I give you a little hint. This circle here, if I were to draw the whole circle, what's the equation of that circle? Anybody remember? Generally, the equation of a circle is x squared plus y squared equals r squared, right? Although this one that would be a circle at the origin. Anyone remember how to make it over there? Yeah.
+2.
Yeah, you got to adjust something or other. +2 something. It's not exactly +2, but anyone? Yeah.
X minus 2 squared.
Yeah. So this would look like this. That's the equation of that whole circle. Now, you don't actually want the whole circle, but I'll leave that to you to think about. See how it goes. This one, I think the integral is going to be weird, so let's just do the setup. This one's a little weird. You should, for the f of x is the hard part here. The f of x, you should solve this thing for y, all right? And that will involve doing a square root at some point. But in order to get my, well, let me just write, I'm going to solve this for y here. It'll be y squared equals 1 minus x minus 2 squared, like that, if you like. I suppose you could do the FOIL there and then do the subtraction, although it's not really going to get much better than this. To solve for y, I take the square root. 1 minus x minus 2 squared. There you go. All right. That's what I should use for f of x. And this can't really be simplified at all, other than FOILing this out and then doing the subtraction, but then it's not much better than that is already. All right, so this is f of x. Right, and then what's the rest of it? The a and the b are just 1 and 2, right? So my integral goes 1 to 2, well, 2 pi out there, x times f of x, which is all of this stuff. Like so. Yes?
You made the 1/4.
The 1/4. Where, what 1/4? Because it's a fourth of the circle. Yeah, any thoughts about that? I actually saw some 1/4 as I was walking around, but I don't think you want the 1/4. Yeah?
Like, since you're revolving it, you're making it kind of like a full, like, I don't know, it's like you're making it the full shape. Like,
That's
it's not
true.
Like you're trying to find that full circle. You're trying to just find that, like, fourth of the circle and then revolve that by making the
Right.
shape.
But I use the equation for the whole circle, so Am I going to get the whole circle?
No, because you're bounding it to the one.
Yeah, right. This is what she said as he was saying it too. Because the integration only goes from 1 to 2, that cuts it off right here. So you're not going to get the whole circle, right? You should also worry though, okay, in that case, am I going to get half of the circle? I used the equation for the whole circle, so am I also going to get this part? Any thoughts about that? The answer is no, I'm not, but why not? This is a tricky question, perhaps.
Because we only include the positive part of the.
Yeah, it's because of the plus minus when I did the square root. So in this step right here, we did a square root, which really you ought to get the top and the bottom, but I only took the top because I only used the plus here. So this really does give you just this part of the circle, right? It only goes up to the 2 because I said only go up to the 2, and it only gives you the top half because I took the plus part of the square root there. Great. Yeah, it's a little strange actually. If you imagine if you actually work this integral all the way out, could I say just multiply that by 4 and that would give me I guess this would be like a donut shape, right? If I took the whole circle and spun it around, it'd be like a donut shape. Is the donut volume four times this? It's actually not, because the outer piece here would have a bigger volume than the inner piece does when you rotate it around. So the volume is weird when this business about fourths wouldn't even work properly because the volumes have different sizes. All right, anyway, that's that. I think actually you can do this integral using a weird U substitution, but I'm not really into that at the moment. All right. So anyway, what we've done so far, all of these have been kind of easy ones, although this one's a little weird just because of the strange function. But we are going to talk about a few simple variations. So the basic formula that I said before, x f of x, forgot the 2 pi x f of x dx. This is specifically for the area under the curve f of x revolved around the y-axis, right? That's the setup for this kind of a problem. And I will just, one more time, if I have a function and this area and then I revolve around the y-axis, right? That's what this was all about. And just one last time, why the x in there and why the f of x in there? The x represents the distance from the center of the rotation, right? So this right here, the x in, x times f of x. The x, the reason it's there, it represents the distance from the axis of rotation. And the f of x, why that is there, represents the height of the shell. All right? This is the height of the shell. All right? So we're going to talk about some variations where sometimes the height of the shell is given in a weird way, or sometimes the axis of rotation is in a different position. And so you'll have to modify this. This is the basic formula sort of for the easy ones, but you have to know how to change this around a little bit depending on the situation. So let's talk about one where it's not just area under the curve of something or other. How about this one? Has the same axis of rotation but a different, different way of making the area. I'm talking as usual about x squared here. This is my favorite simple example function. Only this time I'm not taking the area under the curve. I'm taking the area from here. This is 1 and 2, and this goes up to 4 because it's x squared. I'm taking this area here, all right? And then we're going to rotate that around the y-axis. Around the y-axis. So this is no longer the area under a curve. The x, so in my formula here, v equals 2 pi integral x f of x. The x actually is still going to be x. X represents the distance from the axis of rotation, and that is just x. I mean, when I'm rotating around the y-axis, the distance away from that is x. But the height is weird in this case. The height here, actually, we have, it's kind of like this is more like a biggie minus smalls kind of situation, right? The height of this thing is the top value minus the bottom value. Okay, so in this example, we need to modify this, change this to be the height of this thing, which as usual, I'm going to think of as the top minus the bottom. All right, and it is like the height of that blue segment that I drew over there. And I would find that by doing the y value at the top minus the y value at the bottom. What do you think? Anybody say what this is in this case? In my example? Maybe someone I haven't heard from. What do you think?
4 minus x squared.
4 minus x squared. I like that. The y value at the top there is 4, just because I said so. That's where I decided to cut it off at the top. And then the y value at the bottom of this little segment here is just wherever the curve is. So the height in this example is 4 minus x squared. Yeah. All right. So you have to know how to kind of change the rules a little bit. This is the basic formula, but this f of x just means the height of something, and you might have to figure out what that is. So just to I don't know if we need to actually calculate this all the way out, but it's going to be, this time my integration will be from 1 to 2, the inner to the outer. And then x, just because x is already part of the formula, and then f of x. Instead of f of x, I use 4 minus x squared, like that. All right. These are confusing much in the same way that the washer ones are confusing to set up. You have to think I find this confusing. You have to think sort of very carefully, make sure you're doing the tops and the bottoms correctly. It can be especially confusing when you are doing kind of some examples using the washers and then right away doing some with the shells. It's like kind of similar, but different enough that you might mess it up. Anyway, to do the integral here, I would distribute the x. Let's just finish this off. 4x minus x cubed, right? And that's whatever that is. It'll be 2x squared minus 1/4 x to the 4. Plug in 2 and 1, etc. Whatever the numbers are. I don't know. I said I was going to do it, and then when I was in the middle, I thought, I'm sick of this. And so I decided not to do it anymore. All right? I'm a mathematician, not an accountant or whoever the person is who just like plugs numbers into things all day long. This is not really what I'm into in my own personal life. Nobody is. That's why we have computers. Any questions about that one, though? This is a slightly weird setup. All right. One more slightly weird thing that can happen is we move the rotation axis, okay? And this will affect that x, this x right here, right? This x represents the distance to the rotation axis. If you put the axis somewhere else, you're not going to write x there. You're going to write something else. So let's try one like that. How about I have a straight line, y equals x, my favorite straight line. And I would like to talk about this area under the curve. So here, this is an area under the curve, so actually you don't have to think too hard about the f of x part. It's just going to be that function. It's just the area under the curve. But I'm going to, this is the weird thing, I'm going to rotate that around this axis. So I want to rotate around the line x equals 1. Instead of, usually we do the line x equals 0. That's the y-axis. But this is the line x equals 1 instead. All right? So in our formula, maybe I'll write this sort of in green, because actually this is not the formula I'm going to use. We have to modify some things about this. In particular, what needs to change is the x. All right, it's because we moved the axis to a different location. Like for example, when I start the innermost, my boundary values in this problem are 2 and 3. That innermost point, x equals 2, its distance from the axis is not 2. Like that would be x, but it's not. It's 1 actually. Can anybody say in general what the distance to the axis will be? If I have some point x here, what's the distance to the x equals 1 going to be? Yeah? X plus 1, or is it x minus 1? Or I think it's x minus 1. So this, like I just said, like this number 2, distance is 1 away from the axis here. So in this problem, the distance to the axis is x minus 1. So when we plug into this formula, you're not actually literally plugging in, but we're going to use x minus 1 here instead of x. All right? The distance to the axis is x minus 1 instead of x. This can be confusing to sort of work out in your head, but lucky for us, it's not so hard to just straight up memorize this. So this will always work. This is a fact. If the rotation axis is the line, x equals k, whatever, it's just some vertical line somewhere. Here it was x equals 1. Then can I just say like the x part of the formula must become x minus k. So in this example, the axis was x equal 1. And so that piece of the formula, which usually says x, needs to say x minus 1. Generally, if you have any line x equals whatever, you replace the x in the basic formula with x minus whatever that value is. All right. So can we just set this one up? We don't have to do the integral out, but let's do the setup. This my function here is just f of x equals x, so that's easy enough. So this one, it's going to be 2 pi out there. The integral, I'm going to go 2 to 3. Those are the inner and the outer boundary values. And then inside the integral, it usually says x times f of x. Actually, the f of x I can use as is because this is just the area under the curve. But the x part I changed to x minus 1. So it's going to look like x minus 1 times x, where this x is f of x, and this x minus 1 is the distance to the axis. Right. If you wanted to do the integral, you would distribute, and then it's an easy integral to do from there. All right. I got one more, and then I think that'll do it. Just another one of this same type here. Any questions about that though? Before I try. All right. This one combines both sort of innovations. I had some for you to try, but maybe we will wait until next time, just because it's almost time to go. Let's put that line right on the line. I got y equals x here, and y equals square root x, which looks like that. I want the area between these curves, and I want it to be revolved around x equal minus 1. All right. So it's spinning around this way. This will look like some kind of a funnel type shape, strange, curvaceous inside funnel. All right. So my basic formula, I'm not exactly plugging into this, but this is the formula you should have in mind. You're going to have to change the x part and also change the f of x part. So what do I use for the x part? Well, if you remember what I said before, when the axis is at x equals whatever, the x part should change to x minus whatever. So in this case, it would be x minus negative 1. So when I set this up, it's going to be 2 pi here. I'll talk about the boundary values later. X minus negative 1, right? Which is, of course, x plus 1. And then the f of x part represents the height of a typical point in the region. Anybody want to say? Somebody shout it out. What should I use for the f of x part? It's the top minus bottom, yes. And in this case, yeah.
Radical x minus x.
Radical x minus x, yeah, exactly. Great. Just to, and what about the a and the b here? Apparently the inner point is 0, that's there. I suppose you have to think a little bit about what's the outer point. It's, 1, yeah, it's the intersection of these two curves, which if you couldn't do it by common sense, you could set them equal to one another, although I happen to know this is the number where the x is equal to the square root of x, that would be 1 or 0. So this one is 1. So it's gonna be 0 and 1 like that, all right? This would be like so, right? I don't think we need to do this integral out, but how would you do this if you had to? It's not so difficult. Yeah, you do some kind of a FOIL here, like multiply this all the way out, and then you get, I guess, 4 terms, all powers of x, and then you could do the integrals. I'll just write that. FOIL, then integral. No problem. This one is not a very difficult integral. All right, I think maybe that's good enough for today. I have some for you all to try, but we don't got enough time at the moment. Let me know if you'd like to talk about the homework. I'm going to go, down to my office for the next hour, so I'd be happy to chat about it. See you on Friday.